Okay, so in this video I will be covering three types of the aqueous chemical reactions, which include single replacement reactions, double replacement reactions, and acid-base neutralization reactions. I will also cover how to properly write the molecular equations for precipitation reactions, ionic equations, and net ionic equations. And finally, we'll go over how to properly draw Beaker diagrams for non-limiting type of reactions. Now let's start off first of all with single replacement reactions. Now, as we can tell, there are three types of the single replacement reactions. The main difference between the three types is the fact that a reactive metal reacts with either an ionic compound, a soluble ionic compound, or an acidic compound, or water. Okay? Now we're going to start with the first type so that we can understand the basics and the mechanism of how everything works, and then we'll go over the other two types. Now what we have in general in single replacement reactions is, again, a reactive metal. Okay, this metal that's by itself has to be a lot more reactive than the metal in compound format. The reason for that is because the reactive metal has to displace or kick the metal that's in the compound format out of its spot. It needs to displace it and regenerate this metal as a new product, and then the other product that's going to be generated is a new ionic compound. Now, some of you at this point might be wondering, how are we supposed to actually know whether this metal that's by itself is more reactive than the metal in compound format or not? This is when we actually refer to what we call as the reactivity series of metals. This is the complete list. It starts with lithium over here being the most reactive metal, and it ends with gold being the least reactive metal. We all know that gold is used in a lot of jewelry, and the reason for that is because it's very unreactive, which makes it ideal for that. Okay, so we would be literally comparing the two metals in order for us to determine whether the reaction is going to happen or not. Now, the other thing I wanted to mention is at the back of your periodic table, you should have all of the half reactions, which show all of the activity series of metal. Again, it's the same exact list, so you can pretty much refer to that list. It goes again from the most reactive lithium to the least reactive gold. Okay, so you also have that option over there at the back of your periodic table. Now in this example over here, we have magnesium metal reacting with copper 2 chloride. The first thing we're going to do is locate magnesium and copper on this list. So magnesium is right here, it's closer to lithium, and then we have copper over here, which is closer to gold. Okay, so we know that these two metals actually satisfy our conditions of the metal that's by itself being the most reactive. So over here we will actually generate these two products. So magnesium will displace copper, it will kick copper out of its spot, generating copper as the first product. Okay, and copper is in solid state. And then magnesium pairs with chlorine to form magnesium chloride. Okay. Now I wrote over here that it's in aqueous phase. I will be going over the states of matter of ionic compounds in a little bit in the second page, where I'm going to discuss the solubility rules and when are we supposed to use the solid state or aqueous phase. But I've also gone over the states of matter of like single atoms such as metals and non-metals in periodic trends. If you guys are interested in learning more about that, let me know down below in the comments. The other thing that I'm going to do over here is I'm going to also balance my chemical equation. Now keep in mind, guys, in general chemistry you are expected to write the right formulas of all of the reactants and products. You're also expected to write the states of matter in any equation, and you're supposed to balance every reaction that you write. Now I'm going to balance real quickly right now, but again, if you're interested in learning more about balancing and if you're having difficulty with that, just let me know down below in the comments, and I can make a separate video on that, but because that would take so much time to actually go over, I'm gonna skip that right now. I'm gonna do it the fast way, okay? So I have one magnesium atom, that's balanced. We have one copper, and then two chlorines and two chlorines, so that is actually a balanced chemical equation. Now over here in the second example, I have silver metal, okay, reacting with zinc chloride. Now I need to obviously locate the elements I'm actually considering over here. So silver is over here, it's closer to gold, and zinc over here is closer to lithium. So I actually have a flipped scenario. I have the exact opposite scenario than this example. So the metal that's by itself is actually less reactive than the metal in compound format. Therefore, in this reaction, silver will not be able to displace zinc because, again, it's less reactive than zinc, okay? So in this reaction, these two reactants are not going to react, and therefore my answer should be a no reaction. So I will not get any products in this case, okay? So be careful before you jump to any conclusions or any answers. You always have to refer back to the reactivity series with single replacement reactions. Now in the second type over here of single replacement reactions, we have a reactive metal, okay, reacting with an acidic compound. Now whenever we're talking about an acidic compound, we have to satisfy two conditions. The first condition is we have to have an H+ ion. The H+ ion will always be at the beginning of that formula, okay? So we do have that in this case. The other condition is we have to have an aqueous phase. Now the word aqueous, or the aqueous symbol, just means that this compound is dissolved in water. That's all it means, okay? And all acids and all bases will always be dissolved in water. This is why you always have to have the aqueous symbol. So since we have the H+ ion and the aqueous symbol, we know this is an acid for sure. And the other thing that we need to identify over here is the same exact thing I was talking about over here, which is whether the metal that's by itself is more reactive than the metal in the compound format. Now here's the thing, hydrogen is not a metal, okay, we all know it's a non-metal. However, it does act like a metal, and it is actually part of this list. It's actually listed over here as H2 gas, okay? Because it's positively charged, we do actually consider it as if it was a metal, okay? So over here, again, we will be comparing cadmium to hydrogen, okay? So I'm going to locate my cadmium. Now, cadmium is over here at the beginning, well, at the beginning of the second line over here, so it is closer to lithium than to it is actually farther away from gold compared to the hydrogen, which is closer to gold, okay? So we know cadmium is actually more reactive than hydrogen. So since cadmium is more reactive than hydrogen, we will actually have a reaction over here. We will be producing the right products. So what we end up producing is an ionic compound plus hydrogen gas, okay? So cadmium will displace hydrogen, it will kick hydrogen out of its spot, therefore producing hydrogen gas as a product. And then the ionic compound that gets produced is cadmium chloride, okay? Cadmium chloride. Now the reason why I'm putting a subscript of it 2 is because cadmium has a charge of +2 and chlorine has a charge of -1. And if you refer to your solubility rules, which again I'm going to go over in a little bit, you're going to see that cadmium chloride is actually in aqueous phase. Okay? Now the third type over here says that we have a reactive metal reacting with water. Okay? Now the important part over here is to note that water is very picky. It does not actually react with anything. In fact, it actually only reacts with these 6 reactive metals only, okay? Now, these are not 6 other metals that you have to memorize. These 6 metals are going to be found at the beginning of the reactivity series, so you can always refer to the reactivity series and you can locate them as the first 6 metals, okay? Water has to have very reactive metals in order for the reaction to happen. Now, since potassium is the second one on that list, we're going to actually see that potassium will indeed actually react with water, therefore producing the metal hydroxide and hydrogen gas. Okay, so since potassium is the metal, we're going to actually produce potassium hydroxide as our first product, and that's going to be an aqueous phase. And then hydrogen gas is going to be released, and hydrogen is always exists as 2s because it's a diatomic. It's one of the 7 diatomics. So therefore, we're going to actually write it as H2 gas. Okay. Now, one thing we forgot to do over here is to actually balance our chemical equation. Never ever forget that. We have 1 cadmium atom and 1 cadmium atom, 1 chlorine and 2 chlorines. So we're actually going to add a coefficient of a 2. And then that automatically gives the hydrogen 2 atoms, and over here we have 2 atoms. Now, if I go back to my equation over here, I have 1 potassium and 1 potassium. And over here we have 2 hydrogens, and over here I only have 1 hydrogen and another 2 hydrogens over here. So we have a total of 3 hydrogens. Whenever you have this issue of having like an odd and an even, you need to make the odd even. So therefore we're going to add a coefficient of a 2, so that's 2 hydrogens plus another 2, that's 4. That's and if we go back to the other side, we have to actually include a coefficient of a 2. 2 times 2 is 4, and then for the oxygen we have 2 oxygens and 2 oxygens, so therefore we have a balanced chemical equation. Okay, now we're going to move on right now to double replacement reactions. Okay, now in double replacement reactions, as the name indicates, we will have a double swapping of partners. Okay, remember in single replacement reactions we were only swapping 1 partner. Over here we will swap 2 partners. So we're pretty much going to be swapping all of the combinations in both reactants. Now we typically have over here a soluble ionic compound reacting with another soluble ionic compound, producing an insoluble ionic compound. Now, whenever we're producing an insoluble ionic compound, this insoluble ionic compound is going to be the solid precipitate. This is why we actually name double replacement reactions as also PPT reactions or precipitation reactions. It's because we do actually produce that solid precipitate as one of the products. Okay. Now keep in mind, if we do not produce this solid precipitate as one of the products, we will get a no reaction again. So you need to also be careful when you're predicting products over here in double replacement reactions. And the second product that we're going to be producing is a soluble ionic compound. Now over here we have to refer to solubility rules, just like how we had to refer to the reactivity series with single replacement reactions. Over here we have to refer to solubility rules to determine whether our products are going to be solid or in aqueous phase. Okay. Now, if you actually go to the back of your periodic table, you're going to find the solubility rules. On the left-hand side, you have all of the soluble compounds, okay? And keep in mind that you have to read the entire rule that's listed over there. The reason for that is because they do give you all of the soluble ions, and then they give you the exceptions. So if you actually miss the exceptions and your compound happens to be one of the exceptions, you're going to obviously get the question wrong. So make sure to read the entire thing. So all of these soluble ionic compounds are going to be in aqueous phase except for the exceptions, which are insoluble. Now anything that's insoluble is going to be in solid phase, and again, I'd like to remind you about the same exact thing I just said over here, which is read the entire thing, because again, they give you the insoluble ions, but at the same time, there are a lot of exceptions. In fact, we have exceptions in every single rule, okay? So I'm going to come back to the solubility rules over here. when we predict our products, but let's look at this example over here. What we have over here is lead 2 nitrate. Okay, this is going to be an aqueous compound, so it is a soluble compound reacting with potassium chromate, and again that is an aqueous compound, an aqueous soluble compound. So over here, since we have two soluble ionic compounds, we know it's a double replacement reaction, so we are going to be swapping the partners of all of the reactants. So since lead is paired to nitrate over here, lead now is going to be paired to the chromate. Okay, so our first product is going to be lead 2 chromate. Okay, and that would be our formula. Keep in mind, lead has a charge of +2 and chromate has a charge of -2. This is why we're not going to have any parentheses and no subscripts. And I'm going to leave the state of matter for, I'm going to actually figure out the state of matter in just a second, but for right now, let us actually just predict the second product. Now over here, we're going to get the second product as potassium nitrate. Okay, so potassium nitrate is going to be my second product. Okay, now the one thing I want to point out over here is we always start with the metal. Whenever we're actually forming the products, we're always starting with the metal and ending with the polyatomic nonmetal. Okay, so keep that in mind. So we always start with the cation and end with the anion. So keep that in mind when you're actually coming up with the products. Now, we have to actually go back to our solubility rules and determine which one is soluble and which one is insoluble, okay? Because again, keep in mind, but they're both soluble, these two products are going to be, are not going to exist, and technically this would be a no reaction, okay? So over here, let's look up the lead chromate. Since we're expecting one of them to be an insoluble compound, we could just start looking in the insoluble column. So over here we have carbonates, chromates, and phosphates are generally insoluble except for group 1 elements or group 1 ions and ammonium salts. Okay, since we can see that lead chromate is obviously not one of the exceptions and it does fit the insoluble salts, we can actually give it a state of matter of a solid, okay, since it's insoluble. And then since we determined this is the solid PPT, okay, we can go back to the soluble column and look up the potassium nitrate. Now over here it says that group 1 ions and ammonium ions are generally soluble and no exceptions apply. And the same thing applies over here in rule number 2. It says acetates, nitrates, and chlorates and perchlorates are also soluble. So we can actually see that in both cases, potassium nitrate is actually soluble. So it does actually take the aqueous symbol, okay? And that's how I would figure out whether my products are in solid phase or in aqueous phase, okay? Now the last thing we have to do, since we predicted the products and the states of matter, is we need to actually balance our chemical equation. So we have one lead atom, okay? We have two potassium atoms and one potassium atom. This is why I'm gonna give it a coefficient of a 2, okay? And now since I added that coefficient of a 2, I also have 2 nitrates. So now I have 2 nitrates over here and I have 2 nitrates over here. And the last thing I need to check is I have a chromate ion and 1 chromate ion. So that is actually a balanced chemical equation. Okay. Now over here with acids and bases, this is the third reaction type that I wanted to go over. And over here with acids and bases, the first thing I want to mention is acids and acid-base neutralization reactions are a subtype of double replacement reactions. Now this is super important. The reason why it's important is because a lot of students actually miss acid-base neutralization reactions as being double replacement reactions. As you'll see when you're doing your lab report, you're going to actually see that many of you are going to miss these reactions as being double replacement reactions because you are not able to actually see the products. And I'll talk about that in a little bit. There are two types of acid-base reactions. If we have an acid reacting with a base containing, we have the two types. So one type is when we have an acid reacting with a base containing the hydroxide ion, and then the second type is an acid reacting with a base containing the carbonate ion. Okay. Now, the only difference in the product would be in just the generation of carbon dioxide. So over here, when an acid reacts with a base containing the hydroxide ion, what we end up getting as the first product is water. So liquid water is the first product. And then the second product is going to be a salt. Okay. Now here's an example. We have HCl, hydrochloric acid. We have the H plus ion and the aqueous symbol. So it does actually satisfy the fact that it's an acid. And then we have magnesium hydroxide. And again, we do have the hydroxide ion and the aqueous symbol. So we know for sure it's a base. Now, an acid reacting with a base produces water immediately, so we don't even need to think about that. Okay, so the water does get generated. And then the salt that gets generated is going to be the magnesium chloride. Okay, so we're going to produce magnesium chloride as our salt. Okay, now the other thing we need to do over here is again to balance. Okay. So we're going to start with our metal. By the way, if you're wondering why do I always start with the metal, I do have a priority list by which I balance. So this is why I actually start with metals first, okay? The priority list actually says to go through metals, then non-metals, and then H's and O's. We keep those to last, okay? So we have one magnesium atom and one magnesium atom. We have two chlorines and only one chlorine. This is why I'm going to add a coefficient of a 2, and that immediately gives me 2 hydrogens over here and another 2 hydrogens over here, so that's a total of 4, and I only have 2 over here, so therefore I'm going to add a coefficient of a 2. 2 times 2 is 4, and then I get 2 oxygens and 2 oxygens, so that is actually a balanced chemical equation. Now in the second type, the only difference when we're reacting an acid with a carbonate, a base containing a carbonate ion, is the production of, so the only difference is the production of carbon dioxide, but we are going to still get the water, the liquid water, plus the carbon dioxide, plus the salt. Okay, so we are going to get the salt and the water. The only exception to the rule is the production of that carbon dioxide from having the carbonate ion. Okay. Now over here we have an example. We have hydrochloric acid reacting with sodium bicarbonate. Okay. Now we are going to produce water. If you're wondering where the water is actually coming from over here, we have the hydrogen as the H plus ion, and over here we have the OH minus kind of embedded as the H and one of the O's. Okay, that's where the water is coming from. Then we produce the carbon dioxide from the carbonate, the carbon with the 2 oxygens over here, okay? And then lastly, what we're going to get as our salt is the sodium chloride, okay? And this is why we produce sodium chloride as our last product over here, okay? Now, if you double check everything, you're going to actually see that this equation is actually balanced. We do have 1 hydrogen. Actually, if we go through the priority list, we have 1 sodium and 1 sodium. We have 1 chlorine and 1 chlorine. We have 1 carbon and 1 carbon. And then we have 2 hydrogens and 2 hydrogens over here. And then 3 oxygens, and we have 2 and 1, so that's 3 oxygens. So we do have a balanced chemical equation. Now here's the note that I have in regards to observations. If you guys remember earlier, I said acid-base neutralization reactions are a subtype of the double replacement reactions. And the reason I say that is because we said that a lot of students miss this type because of the observations. Now keep in mind, all acids and all bases are clear and colorless. So you're not actually going to be able to see any difference in the color or the texture of the reaction, okay? The only thing you're going to be able to see is bubbling. Whenever we react an acid with a base, they do actually bubble quite a bit, okay? The bubbling happens because we do actually neutralize the acids and the bases, producing water, and that's where the bubbling happens. And keep in mind, in this type of a reaction over here with the carbonate, you will get even more bubbles because you're producing the carbon dioxide gas. So you're actually going to get a lot more bubbling in this case, okay? The other thing that we need to note over here is the production of heat. If you were to touch that test tube when you're actually running this reaction, you're actually going to feel that the reaction produces heat. These reactions, the acid-base neutralization reactions, are exothermic, so they will be actually producing a lot of heat. And that's another sign of acid-base neutralization reaction. Now, if you get the heat, if you actually feel heat is being produced, or you see the bubbles and you know you're reacting an acid and a base, that is actually a positive double replacement reactions. Keep in mind, in lab, when you're actually filling out your lab report, we will have at least 2 of these reactions, if not more, in the double replacement reactions, and a lot of students again miss those as being positive double replacement reactions. So don't miss writing these 2 reactions in your 14 reactions that you're supposed to actually write for this particular lab report, okay? Now, the last thing I want to go over is the molecular equation, ionic equation, and net ionic equations, and Beaker diagrams of precipitation reactions and neutralization reactions, okay? Now, over here with molecular equations, what we typically do is we typically actually have a regular equation. So if I were to actually give you the example of aluminum nitrate, okay, over here. So we have aluminum nitrate, it's in aqueous phase. Let's say it's reacting with sodium carbonate. Okay, and again, sodium carbonate is in aqueous phase. And I told you to actually predict the molecular equation for this sort of reaction. Now, the very first thing you should be able to identify over here, we have a soluble ionic compound reacting with another soluble ionic compound. So it is a precipitation reaction, so they will be swapping partners. So the first product we're going to form is aluminum carbonate. Okay, you should be able to predict these products. So we're going to get aluminum carbonate over here. Now keep in mind, aluminum has a charge of +3. So therefore, we're going to actually put parentheses around the carbonate, and we're going to give it a subscript of a 3. And since carbonate has a charge of -2, we will actually give the aluminum a subscript of a 2. Okay. Now again, I'm going to wait a little bit to predict whether it's gonna have the solid phase or aqueous phase, but let's come up with the second product. The second product is going to be sodium nitrate, okay? Now if you remember from a couple of minutes ago when we went over the previous example, we saw that sodium nitrate was actually aqueous, okay? If you go back to your solubility rules over here, you will actually see that sodium fits this first category where it says that group 1 ions and ammonium ions are always soluble, so that fits this category. And it also fits the second category where it says that acetates, nitrates, and chlorates and perchlorates are all soluble, so that's why I gave it an aqueous symbol. Now, if we look up aluminum carbonate over here, we're expecting it to be a solid, but let's double check. It says carbonates, chromates, and phosphate ions are generally insoluble, except for group 1 elements and ammonium salts. So it does indeed fit this category, and this is why I'm going to actually give it a solid phase as a state of matter, okay? Now we wrote our products, we wrote our states of matter. The other thing we need to do is balance our chemical equation. So we're going to start with aluminum since it's the metal. So we have 1 aluminum and 2 aluminums over here. So we're going to actually give it a coefficient of a 2. Now we could technically go to sodium, but because this equation is so involved, I don't want to lose track of my balancing. So since I just put that 2, I need to take care of the nitrate. So I have 2 times 3, which is 6 nitrate ions. And over here I only have 1 of them. Okay, so therefore I'm going to add a coefficient of a 6. Okay. So now I have 6 nitrates and 6 nitrates, and now I have 6 sodiums and only 2 sodiums over here, okay? This is why I'm going to add a coefficient of a 3. 3 times 2 is 6, and now I have a 6 and a 6. And the last thing I need to balance is the carbonate. So I have 3 carbonate ions and 3 carbonate ions. Keep in mind that this 3 belongs to the actual formula, so it doesn't count as like a tripling of the carbonate, okay? So now we do actually have a balanced chemical equation. So the molecular equation is pretty much the same exact story as what you've actually been seeing so far. If you write a regular equation that's balanced and has all of the states of matter, this is what we actually call a molecular equation. Now the ionic equation has to take into account how many ions are present in solution. Now keep in mind that if we have any sort of compound that's in aqueous phase, it will break down into its ionic form. If we have a solid compound, that solid compound will stay intact. This is actually going to be my PPT, or precipitate, and it will sink to the bottom of the test tube or the beaker, so it's not going to break apart. So when we're writing the ionic equation over here, I'm going to break everything apart. So I have 2 aluminum, okay, I have 2 aluminum, 3 pluses, and again I have to include the aqueous symbol, okay, and I have 2 times 3 nitrates, okay, so 2 times 3, which is 6 NO3 minus ions for nitrate, and again it is in aqueous phase. And I'm going to add, again, the amount of ions I have over here. So 3 times 2 is 6 sodium pluses. And again, it is in aqueous phase. And I have 3 carbonate ions. And again, it is in aqueous phase. And now I'd have to actually write the products over here. Now, since this is in solid phase, this is our precipitate, I will leave it as it is. So I'm just going to bring it down as it appears, okay? And I'm not going to break it apart at all, okay? I'm going to include that solid phase so that whoever is grading this work could know that I know what I'm doing, okay? And then I'm going to add the 6 sodium pluses, okay, again in aqueous phase. And lastly, we're going to add the NO3 minus aqueous, okay? And that would be my full answer for the ionic equation, okay? Now for the net ionic equation, all I'm supposed to do is cross out anything that appears to look the same on both sides of the equation. So I'm going to start comparing the left-hand side of the equation with the right-hand side, and I'm going to cross out anything that actually looks the same, okay? Now, if we start over here with aluminum, with the 2 Al3+, we can actually see that nothing is similar to that on the product side. Now keep in mind this is in solid phase, so we cannot cancel the ion with the compound, okay? This is why we're not going to cancel anything out over here. But over here we have 6 NO3 minuses, and over here, oops, I forgot the 6, because the 6 actually comes from over here. This 6 actually belongs to the sodium and the nitrate, okay? Now, we need to actually cancel the 6 sodium minuses on both sides. So over here, I'm going to cancel the 6 sodium, the 6 NO3 minus with the 6 NO3 minus on that side. We're also going to see that we have 6 sodium pluses and 6 sodium pluses. Therefore, I'm going to cancel these two also. And lastly, I have the 3 carbonate ion, and again, I cannot cancel that with the solid, so I'm going to keep it as it is. Now, in the net ionic equation, I just pretty much need to bring down anything that did not cancel, okay? So I'm going to bring over here the 2Al3 plus aqueous, and I'm going to bring down the 3 carbonate ions, okay? And I'm going to draw an arrow, and I'm going to bring my solid, the Al2 CO3 solid, okay? And that would be actually my answer over here for the net ionic equation. Now keep in mind, guys, it's really easy to write down the molecular equation, ionic and net ionic equation. You just need to keep track of which one goes in which spot. Now keep in mind, if they asked you on a quiz day for the net ionic equation, you cannot possibly provide them with the ionic equation. And at the same time, if they ask you for molecular equation, you cannot provide them with net ionic equation. The other thing you cannot do is you cannot leave out the states of matter, you cannot leave out the charges or any of the balancing. Everything is important and everything is worth a lot of points. So keep that in mind when you're actually writing down your answers. Now the last thing I want to go over is how to properly draw Beaker diagrams for non-limiting type of reactions. Now keep in mind, the Beaker diagrams are based on the ionic equation. So it's based on the ionic equations that we just did over here. Now what we're going to do is we're going to enter the first reactant in the first beaker, second reactant in the second beaker, and all of the products in the last beaker. So I'm going to take my first reactant. We have 2Al3 plus. Okay, I don't need to enter the aqueous now because this is supposed to be dissolved in water. Okay, this is why we have the Beaker diagrams, because they're all dissolved in water. The second thing we're going to enter over here is the 6NO3 minus. Keep in mind, we do not actually ignore the one we crossed out. The only reason why we crossed it out was because just to come up with the net ionic equation. So don't forget your 6NO3 minuses. Now, as the second the second reactant, we have a 6 sodium plus over here, and we have a 3 CO3 minus 2. Okay, so that would be my second reactant. Now for the product, since we get a precipitate, the precipitate is going to precipitate at the bottom of the beaker, or it's going to sink at the bottom of the beaker. So we will actually draw that precipitate over here, and we're going to actually draw like a half circle indicating that it sinks down there and it does not break into its individual ions. Now keep in mind, this happens 95% of the time or more. So 95% or more of the time, it will stay as a solid and it's not going to break into its individual ions. But there's like a 5% chance or less than that these ions are going to break into solution. So we are going to ignore that 5%. Okay, we're going to just assume that the 95% just stays at the bottom of the beaker, just to simplify things. Now the other thing we need to include is the 6 sodium pluses, and we also need to include the 6 NO3 minuses, okay? And that would be actually your full answer over here. Now keep in mind, there are a couple of things that you need to keep in mind when you're drawing your Beaker diagrams. You need to include the proper ratio. So if I have a 6:2 ratio, you need to include that. It is not okay for you to actually include the 2 as a subscript, okay? That's wrong. A subscript indicates that that is actually part of the formula, as in the case of NO3. Okay, that's part of the formula. That's why it actually goes there. But if I were to actually multiply a number, I'd have to actually include it up there as the coefficient before the formula. Okay, so proper coefficients need to be included. Charges have to be included. Also, you cannot skip on those. And the states of matter have to be included in all of the equations. Now here's the thing. If you remember, I told you earlier that acid-base neutralization reactions are actually considered to be part of the double replacement reactions. The reason why I mentioned that is because if you get a question such as this one, which says hydrochloric acid, okay, reacting with sodium hydroxide, producing water and salt, okay, the salt is going to be sodium chloride, okay. Now what's going to happen over here, if you were to actually draw the Beaker diagram of the product, I'm only concerned about the product because obviously for the Beaker diagrams for the reactants, you would still break down the H plus ion and the Cl minus, you will break down the sodium plus and the OH minus ion, but a lot of students get confused over here with the water and the sodium chloride. They always get confused on what to do exactly with the water. Now keep in mind, water is just going to be represented anywhere in the beaker, and a lot of times we just draw it in the middle of the beaker as liquid water. We do include the state of matter just to re-emphasize the point that water is still there. And because it is actually a significant product in this case. Keep in mind, in other cases, everything is dissolved in water, but it's not an actual product. Over here, in this case, it is an actual product. And then we would just normally, we would still draw the sodium chloride as individual ions as we would normally do that for any ion. So we would have the sodium plus ion and the Cl minus ion, and that would be your answer for a Beaker diagram that involves any acid-base type of situation. Okay? So make sure that you answer these questions carefully, especially when you come to acid-base type of reactions, because that's where a lot of students actually get tricked. And don't forget that the acid-base reactions are actually double replacement reactions, so they are actually going to be included in writing double replacement type of reactions. Okay? Now, I hope you guys learned how to properly write down the products of single replacement reactions, double replacement reactions, and acid-base neutralization reactions. If you guys have any questions about that, email me or write me any comments down below the video, and I will get back to you as soon as I can. Okay, I hope you guys learned everything, and I'll see you in the next video. Bye.